Today, I want to talk about a subject that I have talked about before, several times actually, but I think there's a lot more still to be said about this particular subject in structural engineering, which is about the moment curvature and what affects moment curvature, as well as what are the applications of this very important property in structural engineering. In fact, in my opinion, this is one of the best kept secret in structural engineering. Why I say that is that whenever my new graduate class starts, I ask the students who are already undergraduate, from very good universities. Most of them have either never heard about it or do not have any knowledge about its application and how it is generated. And also, when I meet many engineers in the field, I find that very few are familiar with moment curvature's application, and especially in-depth knowledge about what we can get out of this very interesting and important property. So today I want to focus on several items related to moment curvature. First of all, how is it is different from capacity design, how it is dependent on the confinement, and most importantly, what is it that we can obtain from moment curvature curve and how we can apply it. So it's going to be a long discussion, so probably we will do it in a few parts. So let's start. First of all, let me start with the main basic statement that we have to go beyond the traditional axial flexural capacity that we are normally taught in concrete courses or normally we use for the design of concrete and composite members. Let me start with a very simple structure, and let me start with two applications for this particular structure. The first one is that we have a structure. It's a simple beam, could be continuous, could be a simply supported beam, and we want to design this beam to carry a certain amount of load. Let's say it's a dead load, it's a live load combined. So we will obviously use the dead load, we will use the live load, we will factor them by a code specified factors, and then we will calculate the bending moment. And from that bending moment, then we can determine the reinforcement based on particular code, ACI or BS or whichever we use, and then come out with the reinforcement for bending moment as well as for shear force. And then after that, we can also check the deflection limit. Calculating deflections is something which is difficult to do accurately, and I will come back to that why it is so. But let's say that the basic design can be done easily with the knowledge that we normally get in our undergraduate studies or in our concrete design courses. And for now, let's just only focus on flexural behavior. For the flexural and axial capacity, we can develop a generalized equation which will handle a generalized cross-section, composite cross-section, with arbitrary direction of bending, with arbitrary stress and strain models. And we can develop equations of equilibrium for axial load, for moment about one axis, moment about second axis, or then resultant moment about any axis. So this is fine. This equation can be developed as an equilibrium equation. And this can then be used to calculate, for that particular case, the bending moment. And then from that, we can calculate the reinforcement using the traditional concrete mechanics that we know, parabolic or rectangular stress block, simplified one. And we can come out with the equation, compression is equal to tension, and then we can from there calculate the bending moment capacity both in terms of compression and in tension, which is a simplification of the general equation that we just saw, equilibrium equation. So this is all fine and this can be done. And you can see over there that the capacity is dependent on FC prime, and it's dependent on the neutral axis depth and the stress block A, depending on which code you use, and that one. So this is good. And this can be done. Now, let's go back to the same problem. And this time we say, okay, I am not interested in designing it, but I already have a beam which has been constructed earlier. Or I would like to find the following answers. First of all, what is the maximum load this beam can carry? Not the design load that we designed, because that was factored in many places, including fee factors, load factors. What will happen when it reaches the maximum capacity? Remember, the shear is out of the question for now, for bending moment. What will happen after that? when and where it will crack, how much will it deflect accurately, will it fail in shear or bending? Assuming that shear is enough, we assume it's going to be bending. Can I control how it fails if it is continuous or indeterminate? What is the most efficient way to size it? These are some of the questions that we can ask about this beam beyond the traditional design. And these questions are not easy to answer reliably through the traditional flexural design procedure that we use for new structures. So now there are two ways to do this. One is that we use physical test. We load test it. But the problem is that when we do that, the structure will be broken, destroyed. We can't really use it if we want to go it all the way and get all the answers. The second one is that we use numerical simulation to get the same answers. And that is where we can set up for the experimental setup, we can do like that. And from there, we can get the full load deflection curve, including the maximum capacity, the maximum deflection, and highest moment it will carry, and what happens after the highest moment. So everything is actually on that curve. You can see from that. But the thing is that we can only get this curve through testing. How to simulate numerically is what we are going to discuss today. And this is where the moment curvature will come into play. But let's get back to the limitations of the strength-based design. So strength-based designs are based on the assumption that they are connected to a certain failure criteria, assumed failure criteria, let's say strain at 0.003 or 0.035. The actions are obtained from linear analysis, even though we are expecting the structure to actually go to nonlinearity to some extent. Then the strength design itself provides no information or control on what happens after that ideal or idealized value of the moment capacity is reached. And then no information is available before or after that particular failure criteria limits. So those are some of the limitations that prevent us from doing a full simulation of that beam. Let's say in more detail what happens for a single curvature. We take a cross section, we define a linear strain diagram on that, we calculate the neutral axis location, and based on that we assume stresses because we fix the stress to be 0.085 FC prime, and from there so basically we are limiting the material stress strain curves, both of them which are complete and nonlinear, to a certain value based on this one. So we say, okay, this is fixed at that 0.003, whatever is the concrete strength over there, and also the steel is fixed at the yield point. So based on these two assumptions, we can then calculate what I showed you earlier, the moment capacity for this one. And this is a moment capacity stress resultant. And this is what we do in a flexural design. So basically, we are just considering one idealized or predefined failure criteria where we fix these things and we compute these values. So nothing beyond is known. So if we load the beam and we have this load deflection curve that I showed you earlier from the experiments, then we can't correlate that to the capacity interaction diagrams, or moment diagram, or moment exit load diagram, because we don't know what happened before that, because that curve is based on, or that capacity formula is based on a particular strain value, 0.003 or 335 or whatever is set. So we have only one location available to us, and we don't know what is happening on any of the other moment values which may occur during the loading of this beam. And as we can see from the curve, there are many values. So we have only information about the yield moment or the design yield moment with factored loads and factored capacity. Both of them have nothing to do with reality. So we can see from here that the axial flexural capacity equation does not give us any information what happens before and after the section reaches that idealized failure criteria, which is linked to the factored loads and factored capacity. So this is not going to be useful for us to evaluate the real structure where the loads are real and the actual material properties are also real, not the assumed design values. So that's where the moment curvature comes into play. So first of all, let's define the curvature so that we can use this definition later in our discussion. So curvature can be defined luckily for us, in several ways. First of all, curvature can be defined as the inverse of the radius of bending. It can be defined in terms of the strain and the location of the neutral axis. and also this strain and then K only, and so on, or all the two strains at the top and the bottom. So there are several ways that this curvature can be defined, because it's basically the rotation of the plane, event plane from the original plane, and that rotation can be then expressed in a number of ways geometrically. So this is all based on geometry of the deformed section. Traditionally, structural analysis or strength of materials, we already know that there is a relationship between moment and curvature, which is based on this formula, that moment is equal to stiffness multiplied by curvature. And then the rotation is then the first integral, and then the displacement is the second integral. So based on that information, we can easily see that the curvature is already well established in strength of materials. The only problem is that this is based on a value of E and I, which are based on elastic properties, which is not true for the case of the beam that we just saw, which is going to undergo nonlinearity. So the stiffness is not known or cannot be fixed. And then if we can have this moment and curvature relationship directly, and we can obtain many things from that, and let's go in that direction. So if this is the low deflection curve real that we obtained from that test that I showed you earlier, then we have a low deflection curve which is nonlinear, which means that the moment deflection should also be a nonlinear relationship, and the moment rotation should also be a nonlinear relationship, and moment curvature is also nonlinear, and the material stress strain is also nonlinear. So nonlinearity exists in all stages of deformation: strain deformation, rotation, displacement, and curvature. So we can see from here that everything is step-by-step built from nonlinearity, or is downgraded from nonlinearity all the way. So let's see how we can focus now on the moment curvature, so we can go upwards from there to the low deflection. So if you look at the nonlinearity, you have the material stiffness, and we add the cross-section geometry to material stiffness, we get section stiffness. We add the geometry to the section, we get the member stiffness, and we add the structure members and structure geometry, and we get the structure stiffness. So the stiffness is built up in stages by cumulative effect of each structural aggregation. Material stress strain curve, we know for a fact that they are nonlinear, because we have seen them all the time through the testing. So more concrete stress strain curve is nonlinear, steel stress strain curve is nonlinear, which means that the moment curvature derived from that, and also the cross-section geometry is changing because of the cracking, will also be highly nonlinear, or should be nonlinear. And then from there, the member response will be nonlinear, and the structural response will be nonlinear. So which means that the nonlinearity, if we start with the material nonlinearity, capture it into the curvature, it can go to rotation can go to force displacement. So we can complete the cycle of nonlinearity, and the missing link here is the moment curvature curve, because material nonlinearity is already known from the material test or material curves. So if we do the moment curvature, we can move ahead to the rest of the determinations. That's why moment curvature is so important in this discussion. Coming back, so moment curvature relationship, basically if you look at the diagram from moment curvature, is clearly that the curvature is a ratio between moment and stiffness, and the moment curvature relationship at any given point is the slope of the stiffness is the slope of the moment curvature curve. So we can see from here that this is the first important observation, which we already know. But the benefit now is that if we know the moment curvature curve, we can back compute the stiffness. We don't need stiffness to compute the moment curvature, rather than it's the other way around. That's the benefit that we are going to talk about. Okay, moving on, how do we generate moment curvature curve? In fact, we use the same equations that we used earlier, or same formulation that we used earlier to generate the stiffness, the capacity equations from the equilibrium of a generalized concrete section subjected to generalized bending, generalized stress strain, material stress strain, and configuration. So it can have any number of materials there, doesn't matter. We just sum them all up. And they are all progressively built from strain to stress resultant. So we can see from here the axial load, stress resultant, integration of various materials. moment about one axis, moment about one axis, second axis, and then the resultant moment similar way, or moment about any axis can be determined in the same way. So we have this whole formulation already. The only problem is that previously we used only for one particular stress strain point, which is the arbitrary failure point, failure criteria that we fixed, 0.003 or 35 or whatever the code specifies. But now, so this is what we did earlier. We fixed that. We fixed the strain, and we fixed from there we took the stress strain curve and we fixed the values. But now we are not going to really pick any point on the strain, and we can put corresponding stress for that strain, and we can bring it back to our equation. So this means that now we are allowing the strain to be less than the limiting strain or more than the limiting strain. We are not going to limit ourselves to the capacity design where the strain has only single controlling value of 0.003 or 35 or 38 or whatever that may be. We are now saying that, okay, strain can have any value, and we can determine the corresponding stress from the stress strain models, and then we are freed from the equation, fixed equation, and we can use this equation repeatedly at different strain levels, because each strain is related to some deformation. So we can compute that at multiple points and generate that curve. So if you do that, you can just do the same thing, and now we can satisfy at multiple points, and we can make sure that the equilibrium is satisfied, and then based on that equilibrium we can get back 1 point for each particular strain value that we have assumed or we have got. So that's the difference that we will get. So for PM diagram, we get it for one particular strain, and for this one we get it for multiple strain values and multiple neutral axis variation, but each one of them must satisfy equilibrium. That's the basic condition, that whatever strain we assume, then the depth of the neutral axis should be such that the stress strain curve that we get and the stress resultants we get must come back and satisfy the equilibrium. Based on only that condition, we should be able to generate the whole moment curvature curve until everything fails or the materials no longer are capable of carrying any strain. So that's the basic principle, which is not much different from the strength design. Only difference being that now we are not limiting the strain, we are allowing it to change from 0 to X value, a very large value. So that's how it was done. So it's, and there are many ways to do that. The people have used different approaches to do this. Some people fix the strain, some people fix the neutral axis, some people fix the initial strain, and so on. So there are multiple ways to do that, and we can, and each may result in a slightly different end result. But basically, we are trying to determine an equilibrium, and it's an iterative procedure. It cannot be found immediately. You need to iterate on every strain variation to find the equilibrium that should be satisfied. Let's come to what affects the moment curvature curve. What are the things that will change this curve so that we can understand how we can compute it, and more importantly, how we can control it later. So these are the things that can affect a moment curvature curve, and there are many. The first of all is the neutral. Let's start with the cross section. The cross section size, the reinforcement, and you can see here that we are also using the direction of bending. Will also affect that, because the portion of the cross section responding to that will be different. Then the presence of axial load will affect that, because the equilibrium will be affected by that. And so the higher the axial load, the reduced curvature we might be able to obtain. And then the confinement of the reinforcement, we'll talk about that, the concrete stress strain curve, steel stress strain curve, and the whole formulation. So there are many things, as you can see, all come into this moment curvature curve generation, and changes in any of these will change the moment curvature curve that we obtain. Let's get back to the basic stress strain curves, because that's the starting point, as I mentioned earlier, and see how do they affect and what is it that we can do about that. So basically, we have two materials here. Traditionally, we can have multiple materials. Actually, this can be done for any number of materials, fibers or bamboo or whatever we want to use. All we need is a stress strain curve. So let's say we have two materials, concrete and reinforcing steel. And this one, look at the concrete, then we have steel and concrete. If you put them on the same scale, you will find that they're very far apart. Concrete is such a small figure in that whole stress-strain curve for steel. The steel occupies a very large capacity both in terms of the stress and the strain, whereas concrete occupies a really small portion in that space. And this is very important because we are trying to bring two materials together which have vastly different capacities, both for stress and as well as for strain. And we are going to put them together. So for the purpose of strength design, it doesn't matter much because we assume one single strain, which is quite small in that scale level, and it won't matter that much. But when we are going to change the strain to large values, this will become very important. So that's why we have to go back and see what we can do about this one. So the strength-based moment capacity considers only concrete strength and longitudinal reinforcement. It has no consideration of transverse reinforcement, as you know, because what I showed you earlier is the stress-strain curve. So that's the stress-strain curve of the axial, of the longitudinal reinforcement and the concrete there. The traditional design has no contribution or no way to include the effect of the transverse reinforcement and its stress-strain curve or its capacity or its strength. So that's the important point that we want to make here. But when you move forward and you see concrete, especially, I'm sure every one of us who has gone through the undergraduate or graduate courses has seen the testing of concrete cylinders. And what you might have observed that it always fails in tension. When you apply the force in compression, it actually fails in tension. And that is because of the Poisson's ratio, and the transverse tension is developed perpendicular to the load of application, and you have vertical cracks, and then it explodes in the horizontal direction. And you have seen all of that. If that is the case, then we can clearly see that the compressive strength of concrete is actually a function of the tension capacity of concrete or the expansion of concrete in the transverse direction. So if we can limit that transverse expansion, we could increase the axial capacity as well. And that is the confinement effect. So material ductility, which is the ability of the material to sustain large deformations. If we look at that, concrete is inherently brittle. It breaks very quickly, as we have seen on the sample. But it can be made ductile by confinement, by not allowing it to expand in the lateral direction so abruptly. And reinforcing steel is inherently ductile, but sometimes through manufacturing process, it could become brittle. And one of the examples is the twisted rib steel that some people use, which is now not allowed, which was artificially increase the strength but eliminate the ductile portion. So which means, and also when we heat and cool or we weld the steel, we may make it brittle. So which means both materials, ductility or ability to sustain large deformation or strains can be affected or can be modified. So let's talk about concrete and the confinement. So if you look at the compression test, come back again, and you can see if you press it, basically concrete expands in the transverse direction due to the Poisson's ratio, and then that produces vertical tension, and that simply breaks the concrete. So if we don't allow the concrete to expand transversely or allow it to expand very slowly, then which means that we can increase the ductility substantially. And this is the confinement effect that we are going to talk about, because we are talking about now strain which is going to go beyond the compressive strain which is determined at that point of failure. So how can we confine? You can see easily that if you basically contain the concrete in a cylinder, or even you contain sand in a cylinder or water in a cylinder, you can't compress it. You put water in a cylinder, you try to crush it, it can't go anywhere as long as it is confined. Same is the case for any material. So if you do that, then we can basically use hoop reinforcement. You can use different types of reinforcement, transverse reinforcement, ties, and it basically confines the core of the concrete, which is within the confines of the transverse reinforcement, both vertically and laterally. And this confinement effect is the one that we are interested in because it can help us to increase the strain capability of concrete so that it can kind of help the steel in some way, because right now it's so far. So we can see that vertically confinement can have all these effects. Plus, it also prevents the bars from buckling, which is another important thing, because when we apply compression to the concrete columns or even beams, the compression bars, they will be under compression, and if they are not restrained, they will buckle. So the confinement can prevent both buckling of the bars in compression as well as confine the concrete within that, so it will not expand abruptly or in a brittle manner and will be controlled. So the amount of the confinement or the amount of transverse reinforcement will now govern how concrete will perform under compression, both in columns and in beams in the compressed area. And that is the effect, I'm sure you might have observed already in many places. The unconfined portion is the one on the white curve, the white part of the figure, and the confined portion can be as large as the gray part, as you can see here. So it can take substantially more strain, not only to take more strain, but also carry higher stress when the confinement is peaked. So this confined portion is the one that we are looking at. And to bring this effect into the moment curvature generation, so that when we put transverse reinforcement, its effect can actually be included in the computations, unlike strength design, where the bending direction has no contribution of the transverse reinforcement. So this is the first important thing related to moment curvature curve, which is different, where we can now include the effect of the transverse reinforcement and the confinement. And this Mender model has been there for a long time, and it is still considered to be one of the good ones for reinforced concrete composites. Okay, let's look at now a few columns, for example, as to test our concept. And I'm going to show you a few columns with different transverse reinforcement. So the first one is no confinement. So basically, the functional reinforcement for bending is not confined at all. So the concrete is traditional concrete. Second one is light confinement. So we confine some bars through increased transverse lateral reinforcement, also reducing the spacing. And then the next one is that we confine it heavily and then very, very heavily. So which means that we use large diameter bars, closely spaced, and we completely confine every bar and put a lot of transverse reinforcement. And roughly it will look like that. These are the images taken from ETABS from CSI Detail, where you can change these parameters to get this column confinement. And now let's see what is the effect of this transverse reinforcement on the confinement, so we can really see whether that really helps or not. And this is the difference. You can see here huge difference. The first green line here, the first dark blue line is the unconfined one, and going all the way to heavily confined with very large strain capability. Imagine this one. This is 0.005 and that's 0.05. So the almost 10 times increase in strain capacity, which is very significant because you basically increase ductility by 10 times and increase the strength almost by 40, 50, 60%. So this kind of effect that is kind of observed, is tested, is realistic, needs to go back now to our computations so that we can create moment curvature which includes this effect. And that's the benefit of using the generalized equations for that purpose, where we can now use the modified stress strain curve for concrete. So the ductility can be improved, and the confinement has a lot of benefits. As you can see from here, there are two types of confinement: the rectangular confinement and circular, and also the hoop confinement in circular. So the best one traditionally has been the circular or the hoop confinement, although there's some research indicating that hoop confinement may have some issues. We can do this confinement, and one of the best actually way to confine concrete is put it in a steel tube. So that's why in some countries, in some regions, concrete filled steel tubes are the best option for columns, because they fully confine the concrete throughout the length, and they eliminate the need for providing hoops, which could be time consuming in construction. So steel tubes filled with concrete can have also high confinement effects and high ductility. So concrete is, but if you go back to the stress strain comparison, even after confining well, it is still weaker, although it is now becoming pretty good. It has crossed the yield point and so on, and then it can. But if you look at the steel, high strength steel, it can be high. No, low strength steel can be there, but it's getting better, much better than the completely unconfined concrete. So now they're becoming comparable, and with new concrete coming up, ultra high strength concrete and so on, high performance concrete, this can go even higher. So that's the effect of the confinement and improvements in the stress strain curves. Now, what are the other effects that can modify the confinement? Cross-sectional shape and proportions, circular, rectangular, so on, tension reinforcement amount and location, amount of reinforcement in compression, very important, presence of axial load, amount and distribution of transverse reinforcement, concrete confinement model, and so on. So there's many things that can affect this confinement. Okay, let's see what affects the confinement. And first of all, of course, is the cross-sectional shape and proportions, then the amount of longitudinal reinforcement, and the amount of transverse reinforcement, which is very important, and its distribution, its spacing, and as well as the concrete confinement model that we may use. Thank you.